Was ich Ihnen heute in dem Vortrag kurz zeigen möchte, ist erstmal eine...
What I want to briefly outline is a motivation. Why do we need driver assistance systems on the road to automated system? Because deep learning, artificial intelligence, excellently presented by Mr. Fürst, you now know how it works. I'm going to explain in a concrete example and give more examples how we at Bosch are using deep learning networks for what applications, and I'm going to talk about the challenge of deep learning. That is to get it embedded in a hardware which is running in the car and doesn't need water cooling at the end. And when we break it down, there are three major problems I have to solve with driver assistance systems. The lane markings, we've got that, and this will always be part of it. And then the road edges, if there are no edges at all, when there is a smooth transition, when we maybe have a surface texture difference, this is what we haven't solved right now. We are working on it for future generations. And the other one is whenever I have a border which is 3D, remarkable, that I have a wall, I have maybe flower pots in the city, or I have construction sort of outlines and markings, and there are 3D markings which we need, 3 points we need. The classical, I've already shown, the lane marking detection, and then the boundaries, any boundaries which we use which I can do with structure for motion or Optic Plus, so that I can detect parking vehicles on the edge. When I have a stereo camera, I can also take these signals and measure actually the boundaries of the road, and then the semantic segmentation. We've heard about it briefly, or saw it in one of the images before. So that is the idea, to define a neuronal network that I can tell every pixel what class it belongs to in the image. Red is part of the road, yellow is part of a lane marking, for example, purple is the edge of the road, and another color is the walk next to the road where the pedestrians walk. And that classification requires a wealth of data. I cannot just back up with a simple model, but as Mr. Fürst has explained, the network has to be taught like a small child what things look like.
Ein weiteres Beispiel für die Anwendung von Deep Learning ist die
The application of deep learning is to plan the trajectories. You can take the neuronal network and you train it where it wants to go. That would be the red labels. These are the training data that went into it. And the task is that as a function of the images, you determine where the vehicle is supposed to go. And the input is here the 3 trajectories and the training data, and we can go through an unknown construction site and get information where to go without explicitly learning which of the lanes is the limiting element. A good element, if I want to go towards automated driving in complex situations to support what lane I want to go into.
Schätzung von Sichtweiten.
Now, also range and site estimation. The machine learning algorithms only work when I get a good image. On the left-hand side, you can maybe detect the pedestrian blinded by the light of the vehicle and highlighted in yellow here. And that is a classifier trained to see the vehicle, also to see the vehicle when there is a lot of snow and blurred vision. And maybe we are unlucky and the pedestrian isn't detected. And I think it would be good to know how good are my algorithms actually, or my neuronal networks, or the modules I have, to design an algorithm that gives an estimation on the quality of the vision. And we have trained a neuronal network here in the scene to detect whether there is snow falling or not. Because when you have a strong snowfall, it may well be that certain 3D processes detect an object where there is no object because there are heaps of snow. And another example where neuronal networks can be used as well. And then you see the entrance into a tunnel. And the probability is that there is snow in the vision. Now you enter the tunnel, the probability goes down. The neural net was no snow anymore. And when you leave the tunnel again, then the probability increases again. And that was a test we made with not very many data, but we were surprised how well it worked at the end. Maybe you will have seen that when we are in the tunnel, there is a small peak in the probability going up, which you will see. But it is not error here. But if you look closely, there is a small snow heap here in the tunnel, and that was detected. And it is amazing what these neuronal networks do, and you don't even understand in detail why they're doing it. To get a probability into the network, what actually snow looks like, this is something that you don't realize yet. And another interesting application for automated driving and for functions like emergency braking, for example, when I have a pedestrian in my sight, will it stop at the sidewalk, at the curb, or will it enter the street? Will it step into the street? Maybe I have to brake a little early, or I don't want to get any artifacts into my function. It would be good if we knew what the pedestrian's intentions are. And we have the recurrent neural networks here when you take a short-term memory.
Hier brauchen Sie dann auch im Training eben eine Zeitfolge an Beispieldaten.
And you need a certain training time, because from one image it is very difficult, one frame is very difficult to decide, and you need the whole scene in order to decide, will the pedestrian look towards the car? These are, of course, hints to determine the behavior of the pedestrian correctly. And another very good input for driver assistance functions, and 100% necessary, of course, once we will be going fully automated. So these were examples which point to the camera in the car. There are a lot of other examples where deep learning can be used, neuronal networks. Here, an offline use case, big data is the keyword. We are using 10,000 of hours of sequences for our driver assistance systems. They are available on disks. They are used to identify failures, but they're a gold mine. It's expensive to collect all this data, and in further development, I want to use it, of course. And this is a challenge, of course, in the data to mine the sequence I'm interested in. What can be done is a big network. It must not be in real time, but with semantic segmentation, I know what objects to detect in what sequences, and I can learn also the relative position of traffic participants towards each other, how they are positioned in relation to each other. And then to test a new function on the basis of this. For example, here we have bicycle riders that are actually on the road. I can enter it, cycle on the road, to what distance to the car, and then I get a list of sequences and where this is available in the database. I use the proper data, and then I have an acceleration because that's really a gold mine of data we have. That's one example for an offline use case. Another offline use case where I can use large neuronal networks is domain adaptation. As I said, to train in data is expensive. Then in order to label it, to get training data, we are talking about hundreds of thousands of frames that have to be pixel labeled. That is immensely expensive. We're talking about a lot of euros here per frame, because somebody's maybe sitting 30 minutes in front of the screen in order to label the frames. It can be done more intelligently, but that's not what I'm supposed to talk about it. But what I'm saying is data, that's our gold. And when you can get them embedded, then you've won, because a neuronal network, everybody can download it, can do a showcase, can get an investor, but what you need are the data in order to get it into series. And we, of course, want to reuse the data from one camera generation to the next camera generation. And then you can share feature space and also enter old data to train new data, and so the performance of the new generation can be driven. And such approaches can be used for artificial synthetic data to enter them into the data. The problem of artificial data is when I only use artificial data for training, the network will probably go on the basis of the synthetically generated images and doesn't connect to reality anymore. But the principal modeling of drivers or pedestrians and their behavior, this is something I can well do with synthetic data, and such feature space will see to it that I not only have the features in my target network that run on the camera that really want to then also get ahead the performance in real life. These were a few examples of what we're working on currently at Bosch in our driver assistance systems. Now, my topic is deep learning goes embedded. What about it? As I said, there are huge networks and you can download the performance. They run on GPUs. And in the demonstration, you have a huge computer in your trunk. And I have brought such a GPU graphic card for the current situation, and they use about 250 watts. And the target, when we are talking about a camera that is using not more than 5 watts. So we have a certain target conflicts. We cannot install the GPU behind the mirror, the rear mirror. And so the performance, how do we get them into our assistance systems? And there are a few influencing factors. You can modify GPUs. They calculate the frameworks on loading point, and so you can go to fixed operations in order to limit the range. You can also try to reduce the number of computation sequences and get a more clever architecture, and also the bandwidth that is storage access is limited. When I want to do it embedded in the vehicle, I do a fixed point implementation. What network do I use? There are those that are more efficient than others, that like ShuffleNet, MobileNet, or SqueezeNet, but they're still very large. And I'm going to prune the network, do more intelligent implementation, so that they can run on the camera. Fixed point, again, maybe it's all clear to you, but 32 floating points, of course, have immense resolution. And if I want to go to 8 bits, but in training I have been at 32 floating points all the time, this will fail. So the performance by raw conversion of a 32-bit network to an 8-bit network, this will, of course, reduce the performance. It isn't that easy. But if in the training and in the selection of the network you take this into account, then you can do the 32-bit implementation to the same pixel accuracy of the 8-bit network. And that is the first step. And the second one is the overall architecture, to downsize it. Okay, and as a summary, what have we achieved? And I'm proud of my team. The number of operations in the network which we are using for our current embedded architecture, we have downsized it by a factor of 50, so 15 times less, and the pixel accuracy was kept at the same level, meaning that a network which only has a fraction of watts as a performance intake can be implemented with a performance that I've just demonstrated to you. And that brings me to the end of my presentation. I hope that I could give you interesting application examples of deep learning applications of embedded systems, which is very important when we move towards autonomous driving. And I could only also show at the beginning, and Mr. Fürst said it, we are not going to do a black box and do a CNN, but I think it's a good approach to break it down, and algorithm detection blocks, which you have, which you are knowing, which you have them running in parallel, because this will help us in the validation of data later on when we know where the functionalities are located. And I hope that I could also show that the art of the game in the future will be data handling as such, and how do I get the best performance from the existing hardware? And I think we're doing quite well.
Günter Grohmeier-Ethers, und zwar
Mr. Grohmeier-Ethers, the question of the application. So we have seen it in the video, and you are also in charge of video, as I understand, but the same technology can also be used in radar or in LiDAR. Can you give us a brief insight? Does the reduction of the GPUs also work in this sector? Well, I basically don't see any difference for LiDAR, for example. We are basically in the same domain, high resolution images and the information. So you can basically use it all the same. And we are also using deep learning in radar to extract from the radar raw data to the selection and identification of objects if you're using radar for this. And we also agree with Mr. Fürst, the decision-making at a higher level, that's the essence. How do I decide? How do I assess the whole situation? And this will not be done just by modulation, but where you will be needing artificial intelligence as well.
Müssen Sie nicht auch ein bisschen Performance?
Do you have to bit of performance sort of in store? Mr. Fürst just said that over the air you can even more performance and can play on improved data sets. I'm thinking of my smartphone when I've got a new smartphone. Well, it works excellently, and 2 or 3 years later, I load down new apps, but I did my updates properly, but it slows down, and so does the laptop. And when you want to use the mechanism, then you, I think, have to have a bit more computing power, more hardware than you actually need for the moment right now. So a bit bigger, what do you say? Well, at the end, I think the existing hardware will be exploited to the full. And I think when we do over-the-air updates, we can also transfer bigger networks. It is not so fixed, the hardware, as it might be in another place. But very important, I think, it will always happen in the back end of the training. We will not expand online in the update like a small child that develops while it goes through life. Or maybe you can just add on another computer. Right.